This integral can be solved the hard way with binomial expansion and the power rule, if you like hard labor and gulags. But fellow comrade, there's actually a little something lurking in this problem to relieve you of your misery. It's this, a composite function. Composite functions are like cosine of x cubed, 2x plus 5 raised to the 6th power, and so on. These are all composite because they have an outside and an inside part. Now, we can do integrals involving composite functions using the so-called substitution rule, also called u-Substitution or u-sub because it helps you integrate with composite functions. Terms and conditions apply. For example, take this integral. We first find the composite function within it. Looks like cosine of x cubed. The inside part, x cubed, we will call u. With this shorthand, the integral looks simpler. The only problem is, we can't integrate yet. Our new expression has u's and x's and dx's all mixed together. Let's get rid of the dx. We do this by differentiating step 1 and solving for dx. U equals x cubed. U is a function of x, so the derivative du by dx is 3x squared. To solve for dx, flip the fractions on both sides. Then, multiply du on both sides. This gives dx in terms of du. Here we treat du and dx as their own little variables that we can multiply or divide. Plug this in place of dx. Aha! In the new integral, both copies of 3x squared cancel out, so we're left with cosine u, which integrates to sine u plus c. We're almost done. Our original problem is in terms of x, so we use step 1 again to change the u back to x cubed. Final answer, sine of x cubed plus a constant c. So u-Substitution is this simple. Step 1, identify the composite function. Step 2, differentiate u in terms of x. Example 2, integrate 2x plus 5 to the 6th power. Here, the entire integrand is the composite function, and the inside part is 2x plus 5, so u is 2x plus 5. This simplifies the integral a bit. Next, differentiate step 1 to get du by dx equals 2, or dx equals du over 2. Subbing in for dx, our integral becomes u to the 6th times du over 2. The power rule then gives u to the 7 over 2 times 7 plus c. Subbing back step 1 gives the final answer here. Next, a harder example. Here, the composite function is x squared plus 1, all to the 5th power, so let u equal x squared plus 1. Differentiating u gives du by dx equals 2x, so dx equals du over 2x. Substitute. Simplify by canceling one copy of x. Uh-oh. There's x squared left over that doesn't go away, so we need to change the extra x's into u's. Conveniently, u equals x squared plus 1 relates x squared in terms of u. X squared is just u minus 1. With this relation, our integral becomes u minus 1 times u to the 5th times du over 2. Now, pull out 1/2 and distribute the multiplication, and use the power rule to integrate. And we get 1/2 times u to the 7 over 7 minus u to the 6 over 6, plus a constant c. Since we want an answer in terms of x, we just sub in x squared plus 1 in place of u. And we have our answer. Here's a few more substitutions to practice. In the first integral, the most complicated thing looks like the exponential. Its job is to exponentiate the sine of 5x. so u is sine of 5x. Second one, again look for the most complicated composite thing. Cosine squared is not so complicated compared to cosine of sine of cosine, so we make u be sine of cosine. Third, ln x looks more complicated than x, so let's let u be ln x. This doesn't look like a composite function, you say, but it's there, just secretly as 1 over ln x. We can also integrate tan x. The trick is to realize tan x is sine over cosine, so like the previous problem, we make u the bottom part cosine x. If this fails, try u equals sine x, and if that doesn't work, just give up.